Alright, so we want to prove that if fx is an infinite set, then the cofinite topology is t1 but not 2, t1 but not t2, and it's first countable if and only if x is countable. So this is a classic case of two exercises in one, but anyways, let's do it. Okay, so we have the cofinite topology, so remember tau is the collection of all subsets u of x such that either U is the empty set or the complement of U is finite. Okay, so we want to prove that it's T1. So choose x, y in x such that x is not equal to y. We can do this because x is an infinite set, so it obviously contains two elements. Okay? Let U be the set x, but without the element x. Okay, I'm sorry that I'm using the same letter for the set and the element, but what can you do? Besides not do that. But anyways, so U, the complement of U is x, or rather, the size of the complement of U is the size of the singleton set x, which is 1, which is finite. So U is an element of the topology, cofinite topology. By construction, x is not in U, but y is in U. Hence, tau is T1, because that's what it means to be T1. It means that given x and y, which are not the same, then there is a set which there's an open set which contains y but not x. And you can choose, it doesn't, like, you have choice of that. You could also, by this argument, find an open set which contains x but not y. Alright, so that's what it means to be T1, and so we've proven that it's T1. Okay, so what does T2 mean? T2 means that if you're given any element x and y, which are not the same, then you can find disjoint open sets such that x is contained in one of the open sets and y is contained in the other open set. Okay, so let's prove that that's not the case. Let x and y, well, we'll use the same x and y from before. So let U1 and U2 be open sets such that x is in U1 and y is in U2. Then there exists sets F1 and F2, which are subsets of x, such that both F1 and F2 are finite, and then U1 is the complement of F1, and U2 is the complement of F2, because that's what open sets are. They're finite complements. Alright. Then, okay, so U1 intersected with U2. What is the set? Basically what we're going to prove is that this intersection cannot be empty. Meaning there has to be something in this intersection. And if that is the case, that there must be something in this intersection, regardless of how we choose U1 and U2, then you can't find open covers of x and y respectively, which are disjoint. Okay, so anyways, this intersection, so this is x set minus f1, we take the intersection with x set minus f2, and well, wait a minute. No. What am I doing? Okay, so this is f1 complement intersected with f2 complement. And so this is the complement of the union. There's a lot of set operations that are useful in just basic algebra of sets is really useful in topology. It's also useful in measure theory. So hopefully, let's see, with this being chapter 4, if you've gone through chapters 1 to 3, then hopefully this is not too new. But these are things that should be really on you should have on the back of your hand and just have ready to use. But yeah, intersection of complements is complement of the unions. Okay, so if we look at the complement of F1 union F2, this is not empty. And why is it not empty? It's because the size of X is infinite, and the size of F1 union F2 is going to be, well, it can't be bigger than the size of F1 plus the size of F2, which is strictly finite, because F1 and F2 are both finite. So, there do not exist open sets U and V in tau such that X is in U, Y is in V, and U intersected with V is empty, because if you take any open cover U of X and any open cover V of Y, then U and V intersect. Alright? So thus, tau is not T2. Okay, so that's what we want to prove. That cofinite topology is T1 but not T2. And that finishes the first part of this exercise. And now we get to move on to the second part. Okay, so let's see here. The topology is countable if and only the topology is first countable if and only if X is countable. Okay, so for the next part, suppose X is countable. I'm going to abbreviate it like this. Okay? So fix some element X in the set X. We must find a countable neighborhood base for tau at the point X. That's what it means to be first countable. It means that for every point in X, there is a countable neighborhood base for the topology at the point. Okay, so since X is countable, let xn, where n ranges over the natural numbers, be the elements of X, which set minus X. So the set X contains the point X and then X1 through X2, X3, X4, etc. So let Vn be X, but we remove the first. Vn is going to be, we take X and then we remove X1 through Xn. So X set minus the union from I equals 1 to n of xi. And let eta, or fancy, no, this is fancy n. because that's what we use for neighborhood bases, I guess. So this is going to be the collection of all VNs where n is a natural number. All right? I claim, I alluded to this before, that n is a countable neighborhood base for tau at x. Clearly, n is countable because we defined it to be a countable set. Vn, n ranges over the natural numbers, which is a countable set. So n is countable, and each Vn is a neighborhood of x. Because each Vn, you remove x1 through xn, and the set x1, x2, x3, etc. does not contain the point x. And so for each of these Vn's, we're not removing the point x. And so Vn is indeed a neighborhood of x. It's in fact an open neighborhood, but I don't think that matters in this definition. So next, let U be a neighborhood of x, any neighborhood. So any open set containing x. So an open neighborhood. Let U be an open neighborhood of x. So x is contained in U, and U is an element of the topology. Then U is going to be F complement, where F is finite. Since, let's see here. So X is in U. X cannot be in F. So F is a subset of the union from I equals 1 to n of xi. Alright? And now let capital N be the max of all the indices n in the natural numbers such that xn is in F. N is finite since F is. And so not only is n, so n exists, and in particular is finite because F is finite. F is a finite set, so there is some maximum there. Alright, so then F is contained in the union from I equals 1 to capital N of xi. So here, oh yeah, it's Halloween. Woo, spooky. Alright, so we have F is contained in this union. So if you take the complement of both sides of this, it reverses the inclusion. So we have Vn is by definition the complement of the union from I equals 1 to, no, this is V capital N. This is the complement of the union from I equals 1 to capital N of xi. And this is contained in F complement, which is U. So there exists a Vn in particular. Well, so Vn is in N, and X is an element of Vn, which is a subset of U. Thus, N, fancy N, is a countable neighborhood base for tau at X. Because, yeah, that's what we need for that's what we need for this to be a countable. That's what we need for n to be a neighborhood base. We need that Oh yeah, that's the other thing. The other condition is that it consists of elements of the topology, so it does consist of open sets. So let's see here. Do we mention that? Yeah, so we said that each Vn is an open. Well, no. We just needed each Vn to have X in it. Well, it's definitely one of those, and the Vn satisfy both, so who cares? But in any case, what we've proven here, the main thing, the tricky part, is proving that for any open set U containing X, there is an element of the neighborhood base V such that X is contained in V, which is since X is an element of V which is contained in U. And that's what we've proven, because V sub capital N does that. And therefore, we've proven that this is a countable place for tau at X. Thus, tau is first countable. Okay, so we've proven that if X is countable, then tau is first countable. So that's one direction, and now we get to prove the other direction. Alright, so the way that we're going to do this is suppose X is not countable. Let N be a countable collection of open neighborhoods of X, where X is just some element of X. And again, we're going to write N is collection of Vn's, where N is a natural number. And Vn is going to be Fn complement, where Fn is a finite set. Right? We can do this because it's the cofinite topology. Okay, then what do we know? Let's set F to be the union from n equals 1 to infinity of Fn. This set is countable because it's a countable union of finite sets. And a countable union of finite sets must be countable. Furthermore, X is not an element of F because X is not an element of Fn for any n, because X is contained in Vn for every n. Okay, so, alright. Oh, wait a minute. Oh, did I mess this up? Okay, let's think about this. Cofinite sets. No, this is okay. Cofinite means a complement is finite. Or, these are complements of finite sets. Okay. Since X is not countable, the set X set minus F is infinite, because F is countable and X is uncountable, so it's not infinite, so it's infinite. So now choose Y to be an element of X which is not contained in F, such that Y is not equal to X. And we can do this because X minus F is infinite, so it contains more elements than just the element X. So for example, it contains this element Y. And let U be X, or let's see here, it's going to be, we'll take F and we'll union it with the element y and take the complement, and this is going to be u. Then x is in u, since x is not in f and x is not equal to y. However, for all I in the natural numbers, y is not in fi. So let's see here. So what does this tell us? So then y is in vi, which means that vi is not a subset of u, because u does not know. U contains... Right, okay, u does not contain y, but vi contains y. So vi contains an element which u does not contain, so therefore vi cannot be a subset of u. Thus, no countable collection of open neighborhoods of X satisfies the neighborhood base condition for tau at X. Because it would need to be the case that for any neighborhood U of X, there is a element V in the neighborhood base such that X is contained in V, X is an element of V, and V is contained in U. However, we've shown you can always find some U which does not contain any element of this countable set. So therefore there is no countable collection of open neighborhoods. Or there is no countable neighborhood base. Okay. Thus, there is no countable neighborhood base for tau at X. Or in other words, let's erase that and replace it with what we want. Thus, tau is not first countable. Okay, so we've proven that if X is not countable, then tau is not first countable. So contrapositively, if tau is first countable, then X is countable. And that proves the other direction that we wanted. So hence, tau is first countable if and only if X is countable. And this finishes the exercise.